Welcome to the tutorial 11, resistance, capacitance and electrical circuits. So in this first question we have two metal objects with a charge of 70 picocoulombs and negative 70 picocoulombs. This results in a 20 volt potential difference between the two. We're asked to find what the capacitance of the system is. If we change the charges, what would happen to the capacitance, and what is the potential difference when we change those charges. Okay, so for the first question, A. We have to find the capacitance of the system. So remember that capacitance is the charge divided by the potential difference, delta V. So we can easily work out what that is. The charge is 70, just looking at the magnitude of both those charges, 70 picocoulombs, and the potential difference is 20 volts. So pico is by 10 to the minus 12, so we have 70 by 10 to the minus 12 divided by 20. That gives us 3.5 picofarads. Great. Okay, so that's the first one. Quite easy to answer. Okay, question B. This has got a bit of a trick to it. If the charges are changed to 200 picocoulombs, then what's going to happen to the capacitance? Well, it turns out the capacitance is independent of Q. So remember that the capacitance, the equation for capacitance is this: epsilon naught A divided by D. So you can see there's nothing there on what the charge is. So the capacitance is irrespective of the charge. So therefore, it doesn't change. The capacitance is equal to 3.5 picofarads. So that's a trick question. So what does the potential become then? Well, we still just use our delta V equals Q on C. That's a rearrangement of the first equation. And now we have 200 pico, so 200 by 10 to the minus 12 coulombs divided by the capacitance, which hasn't changed, 3.5 by 10 to the minus 12. That equals 57 volts. Okay, so all that happens if we change the charge, we change the potential difference between the plates, and the capacitance doesn't change. Okay, so that's a nice question. Next question. The capacitor in this figure here has a capacitance of 25 microfarads and is initially uncharged. It's uncharged because it's a switch there that's open that doesn't allow current to flow, which means there's no charge build-up on the capacitor. The battery provides a potential difference of 120 volts. After the switch is closed, how much charge will pass through the capacitor? Well, the charge will flow, so let's just say this. The charge will flow when delta V across the capacitor is equal to delta V across the battery. Okay, so that's when, remember that C equals Q on delta V, and we need to find Q, so we need to rearrange that. Q equals C delta V, to delta V. We put in our values now. We have 25 microfarads, 25 by 10 to the minus 6, multiplied by the voltage. So once we reach the voltage of the battery, it's 120 volts. We get an answer for that as 3 by 10 to the minus 3 coulombs. That's our answer. Okay, so that's how a capacitor works. You basically build up charge until the potential drop across that is the same as the battery, because there's no other devices in there to drop the potential. And then we can work out what the capacitance is by just using this expression here. Too easy. Next question. This is an interesting question. In this situation here, so we have a figure. Look at figure A. It gives the magnitude of the electric fields that are set up by a battery along a resistive rod of length 9 millimeters. So that's this this guy here, this rod. So that's 9 millimeters. Now, the rod consists of 3 sections of the same material, but with different radii. So that's not really shown in the diagram there. If I wanted to draw that, I would say it looks more like this. There's your battery. You've got a rod that kind of looks like this, with different diameters. Now, they could be different, and then it comes back around. And we're going to be able to work out what the diameters of the different sections are by having a look at what's happening to the electric field within them as a function of the position. So you can see there's three regions. There's this region here, and then there's this region here, and then there's this region here. And they all got different radius because the resistivity is going to be the same in all those regions. So it's the same material. So let's just say that for a question. Well, the resistivity is constant. Okay, which means resistivity 1 equals resistivity 2, which equals resistivity 3. So that's the first thing we have to note. It's the same material. Now the current flowing through all those sections, so let's write this down. The current through each section is constant also. So I1 equals I2 equals I3. Okay, that's just saying that current's flowing in through here, and the same current flows through all sections of the resistor, and then it flows out of the resistor here. So that's I. Right. So we also have a couple of equations here. We know that the resistivity is the electric field divided by the current density, J. And we also have J equals the current over the cross-sectional area of the resistor. So we're going to have to, the things that we have here, are we know something about the radius, or we're trying to find something out about the radius. We know the current's constant. We know the electric field as a function of where it is in the resistor from our graph. So we know the resistivity is constant. We should be able to rearrange these two equations here to figure out a relationship between the radius and the electric field for each of the sections. So we can say, if we combine these two expressions here, I'll just erase that little wiggle. If we combine these two equations, we get something that says the resistivity is equal to EA on I. So this means that resistivity times I equals E times A, and that equals E pi R squared. So now rho times I is a constant. Okay, that's just some value. It's the same for all sections of the rod. So therefore we can say, well, let's just rearrange this guy and say rho I over pi equals E R squared. This section here is constant value. So we can therefore say that for the first section, the electric field times the radius squared is equal to the same in the second, because this value is the same in both regions, E2 R2 squared, which equals E3 R3 squared. So we're going to be able to find something that we do know is that we do know what R3 is. We're told in the expression in the question up here that the radius of section 3 is 2 millimeters. So some other information we have is R3 equals 2 by 10 to the minus 3 meters. Great. So we can now find R1. So let's find R1. We can just relate E1R1 squared equals E3R3 squared. So therefore, R1 squared equals E3 over E1 R3 squared. So we have all of that information. We know the ratio from our graph. We know what the ratio of E1 to E3 is. So E3 to E1, sorry. We can work that out. It's just going to be E3 is basically 1.5 and E1 is 2.5 if you look at the graph. And we have R3 squared is just going to be 2 millimeters. We can just leave this in millimeters for now. It might make things a bit easier. Squared. So that's R1 squared. So to get R1, we go square root of 1.5 over 2.5 times 2 squared. That's going to give us an answer in millimeters, and it comes out to be 1.55 millimeters. So that's R1. Okay, so we can do the same process to find out what R2 will be. So we just now go E2 R2 squared equals E1 R1 squared. So therefore R2 equals, by the same argument, it's going to be E1 over E2 R1 squared. Put the values in for that, and you get 2.5 over 4, and it's 1.5 for R1, which we just calculated in the last question, and we get an answer for that, which is 1.22 millimeters. Excellent, that's our answer. So that's just exploiting the fact that we have a couple of equations up here, and that the resistivity is the same through each section, and that the current flowing through will be the same for each section. Great. Okay, so we have here a very, very simple circuit, battery connected to a resistor. Figure B shows the increase of the thermal energy in the resistor as a function of time. So there's some dissipation of electrostatic energy here, electrostatic potential, in the form of thermal energy. And you can see there, you're getting rid of some thermal energy as a function of time. And the vertical scale set by a couple of constants there, and so is the horizontal, is also set by some constant. We're asked what's the electrostatic potential across the battery, so the voltage difference. So if we look at the slope of so the slope, I'll write this down, the slope of a energy versus time gives us power. Okay, so if we look at this graph here, we find the slope of the graph, we're going to get the power. And the power is going to help us find out what the voltage drop across this resistor is. Remember, the thermal energy comes about because we're dissipating the electrostatic potential energy of the battery across that resistor. So we just go power equals rise over run of the graph, and that is, let's say, the rise is, from here to here. The graph is 2.5 by 10 to the minus 3 joules. The run of the graph is going to be this distance here, and we know that to this point here, to TS, that's 4 seconds, so to here it must be 5 seconds. So 5 seconds on the bottom. Joules per second is going to be in watts, and we get a value that is 5 by 10 to the minus 4 watts. So that's our power. So that's the power that's being dissipated across the resistor in the form of thermal energy. So we can, we've got, the old P equals IV, and we also have that I equals V on R from Ohm's law. we can then say that P equals V squared on R. Okay. And we want to find V, so we need to rearrange that equation, and we get V equals square root of P times R. That's going to give us our voltage, or the potential difference across the resistor. So that's going to be the square root of 5 by 10 to the minus 4 multiplied by 20 for the resistance. Gives us a value of 0.1 volts. Excellent. So a couple of concepts there, but in the end, quite a simple question to solve. Okay, so there's a couple of questions here, a couple of different circuits. We'll look at the first one, and then I'm going to give you the answers for the second one, but you can work it out yourself. So what you have here is a setup that has the first one, so we're talking about this circuit here. You actually have a couple of resistors, R2 and R3, in parallel, so these guys here are in parallel, and then they're in series with this bad boy here, R1. So we should be able to find, first of all, this is what we always do, find the equivalent resistance of the combination. So what's the total resistance of that circuit? We can then find the current that flows through the combination, and then we can find the voltage across and the current through each resistor. So that's how we solve these problems. So let's find out what we have here. Well, we know that, let's look at the parallel combination. So let's look at the parallel combination of R2 and R3. I'm going to call that R2, 3, like this. So that would be, because they're in parallel, we say 1 over R2, 3 is equal to 1 over R2 plus 1 over R3. Okay, and that, if you do a bit of nice algebra, you'll see that R2, 3 is equal to R2 times R3 over R2 plus R3. I'll leave that to you as an exercise. So we have an equivalent resistance of those two resistors, R2 and R3, that can be found by that. And if you put the values in for this, if you put in, you've got 4 ohms for R2 and you've got 6 ohms for R3, the equivalent resistance comes out to be 2.4 ohms. So if you put in those values. So now we have a resistor that's this guy, R23, that has a value now. We can replace those two resistors with one single resistor. So then the total resistance of the circuit is going to be R1 in series, so plus R23. Now we know that R1 is 2 ohms, and now we know that R23 is 2.4 ohms, so we get 4.4 ohms. We've answered the question. We now have the total resistance of the circuit. This allows us, for the next question, to figure out what's the total current flowing through the circuit. Well, we know that so we'll just call that I1. So we've got I1 here, we've got I2 here, and we've got I3 here. So remember, we've got that flowing in, and we've got these guys flowing out this way. Okay, so we can find out what I1 is flowing through the circuit. I1 is just the voltage of the battery over RT. That's 8 volts divided by 4.4 ohms. That comes out to be 1.8 amps. So we've got a total of 1.8 amps flowing through the circuit. Okay, we need to find out how that 1.8 amps is distributed between I1, I2, and I3. Well, we know I1 is 1.8 amps, and we know that I2 plus I3 is going to be 1.8 amps also. But we have to see how that's going to work. So we can, first of all, let's find out what the voltage. So we're asked to find the voltage drop across each of these resistors as well. So for R1, we know the current flowing is I1. It's 1.8 amps. So therefore, V1 is going to be the current times the resistance, so I1 R1. So that's 1.8 times 2, which is 3.6 volts. So we've got 3.6 volts dropping across resistor 1. What about the combination of R2 and R3? So we know that the voltage drop across those will be equal because they're in parallel. So we know then that V2 equals V3. So the voltage drop across those guys are equal. That's the definition of your parallel circuit. And so therefore, you know, I2, R2, that's the drop across V2, is equal to I3, R3. Okay, so then we get, from that one, we're going to get that I3 equals R2 over R3 I2. And so that's an equation. And we also know, we know that I1 equals I2 plus I3. That's the you know, when we're looking at this node here, that's what's actually happening. We're getting I1 flowing in, I2 and I3 flowing out of it. So therefore we can say, if we just substitute I3 into this equation here, we get I1 equals I2 1 plus R2 over R3. With a bit of creative algebra. We can solve for I2 then, so therefore I2, just by rearranging that expression, is going to be I1 divided by 1 plus R2 over R3. And that's equal to, when you put the values in, you get 1.1 amps. So we know the values of the resistors. Okay, so we know the current flowing through I2 now is 1.1 amps. So it's pretty trivial to figure out how much is flowing through I3 because we've got a total of 1.8 amps flowing in and we've got 1.1 going to I2. Therefore, I3 is just going to be I1 minus I2. And that's going to be 0.7 amps. So now we have the current flowing through all of them. And the last thing we're asked to do is find the voltage drop. And we know the voltage drop across them is equal. So we know that the voltage drop across R2 and R3 is equal. We also know that the total voltage drop, so from here to here, is 8 volts. So that's 8 volts. The voltage drop from here to here, we worked out earlier as being 3.6 volts. So the voltage drop across here has to be 8 minus 3.6. Okay, so that's going to be 4.4 volts. So V2 equals V3 is 4.4 volts. No worries. So we've got everything. We found the voltage across and the current across each resistor. Now for this next circuit, so for this circuit here, you can see, I'm going to leave this for you to do, and I'll write the answers up. But you can figure out an equivalent resistance for this by saying 1 over, because these are all in parallel, 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And you should get an equivalent resistance once you make sure you invert this in the end. Otherwise, you get 1 over the resistance. So the equivalent resistance will come out as being 1.09 ohms. Then you're asked to find the current through it, so that would be the answer for A. The answer for B is going to be, you're looking for the voltage as you go, so it's going to be, the current is going to be voltage divided by R, which is going to be 8 over 1.09, which is 7.3 amps. Okay, so there's going to be a total of 7.3 amps. Now, when you know that the voltage drop across each one of these is equal, okay, so there's the same voltage drop across all those, they're in parallel, then what you end up with is that I1 is equal to 4 amps, I2 equals 2 amps, and I3 equals 1.3 amps. That works out nicely. All of these guys add up to this, so the current is flowing correctly. Also, R1 is a lower resistance, so it should have more current flowing through it, and that's what actually happens. So that's the answer to that guy. So I'll let you work through that yourself. This is an example of Kirchhoff's loop rule. To solve this, it's kind of complicated looking circuit. We can see we've got batteries that are facing this direction, we've got batteries that are facing back that direction, we've got a few different resistors in there, so we have to really consider how to solve this using the voltage loop rule. So first of all, what we do is we've got I1 flowing in this loop, and we're going to have I2 flowing in this loop. And the loop direction you choose to be this direction for loop 1, so that's loop 1. And you've got another loop going this way, which is loop 2. And if we consider both of those guys, we're going to be able to find what the current flowing through each loop is, and therefore the current through each resistor. We're going to be able to work out the power supplied by each DC source and also the power dissipated in each resistor. And we should find that the power supplied by the batteries is dissipated by all of the resistors. That has to happen, otherwise we haven't dissipated all of the electrostatic potential when we get to the other side of the circuit. So we are going to employ Kirchhoff's loop rule. Kirchhoff's loop rule. And that says that the sum of the drops, voltage drops, around the loop equals 0. Okay, so we're gonna, that says loop, not loof. Sorry about that. So we consider one loop at a time. So if we have a look at this first loop, there is going to be, let's have a look at it. This guy here, because the loop is going from the negative to the positive terminal of the battery, you're going to have a voltage gain there, so that'll be a gain. Now, the current's flowing through the resistor in the direction of the loop, so therefore there's going to be a voltage drop across here. Again, this is going the right direction, so there's going to be a positive gain from the battery there. You're going to get a voltage drop across this guy. You're going to get a voltage drop across this guy. You're going to get a voltage drop across this one because the negative terminal, the loop's going the opposite direction. It's going from here to here, so that's going to be a negative through that battery. And then the annoying thing here is that there's going to be a contribution from loop 2 through this resistor here, and that's going to be pushing back the other direction. So you're going to get a positive contribution from loop 2 with current I2. So let's add up all of those voltage drops across the circuit. They have to be equal to 0. So we're going to get V1, which is the 8-volt battery, and it's positive. We're getting a voltage drop of I1, R1 across that resistor. We're getting a voltage gain across the second battery. We're getting a voltage drop, I2, R2, across the resistor. We're getting another voltage drop across the next resistor. So that's, sorry, I've stuffed up there. Sorry about that. Start again. So let's just use a loop rule. Sum of the voltages equals 0. So let's start again. We've got a voltage gain across the first battery. We have a voltage drop across the first resistor. We have a voltage gain with the second battery, and we have a voltage drop, I1, R2 across that resistor. We have a voltage drop across the third resistor. That's a 3. We have a voltage gain, remember, from that green part pointing back upwards from the other loop. So that's going to be I2, R3. And then we have a voltage drop from the other battery because it's facing the other direction, so V3. That equals 0, so that all comes to 0. So we can put some values in now. We get 8 minus I1 plus 4 minus 2I1 minus 2I1 plus 2I2 minus 4 equals 0. So let's get all our terms together. We're going to get 8, because we go 8 plus 4, 8 minus 4, so we get 8 minus 5I1 plus 2I2 equals 0. If we do some rearranging and divide through and to get rid of some common denominators, we get I1, solving for I1, we get I1 equals 2/5 I2 plus 8 on 5. So that's our first equation. Can't really solve that, we've still got two unknowns, I1 and I2, so we have to use our second loop, so loop 2. And we look at that one, if we look at the second loop, we're going to get V3 as a positive voltage. We're going to get a voltage drop of I2 R3. We're going to get a voltage gain coming back from loop 1 again, in the same way that we got it from the in the first loop, I1 R3. So there's going to be a backwards contribution through R3 from the first loop, minus our voltage drop across this 6 ohm resistor, which is I2 R4, that goes to 0. So we get 4 minus 2I2 plus 2I1 minus 6I2 equals 0. And then we get 4 minus 8I2 plus 2I1 equals 0. And that goes to our final equation, I2 equals I1 over 4 plus a half. So now we have two equations with two unknowns, so we should be able to solve that. So if we just substitute one into the other, and what we're going to do is just substitute one into 2. So if we just go 1 into 2, we get an expression that says I2 equals 1/4 2/5 I2 plus 8 on 5 plus a half. So you can see now we've got rid of I1 out of that expression, so we're going to be able to solve for I2. If we rearrange this guy and we get the algebra right, we should end up with an equation that comes out as, with solving for I2 here, which should give us I2 equals 1 amp. Okay, so all we've got to do is just solve the algebra here. I'll leave that to you as something to do. And we get I2 equals 1 amp. So we can substitute that back into the equation. Let's put that into equation 1. So into 1, let's write it here. Into 1. We know what 2 is, so we can just plug it back into 1. I1 equals, remember it was 2/5 I2 plus 8 on 5. We put 1 in for I2 and we get 2 amps. Okay, so now we have what I1 is as well. This is really good. That was the first part of the question, find the current through each resistor. Okay, so the current through them is, if we think about this carefully, there's 1 amp flowing through the first loop, 2 amps, flowing through the first loop, and 1 amp flowing through the second loop. So therefore, R1, so the current through R1 is going to be 2 amps. The current through R2 is also going to be 2 amps. The current flowing through R3 is a bit tricky because it's got 2 amps flowing one direction and it's got 1 amp flowing back the other direction. So that means we're going to end up with 1 amp total flowing back through R3. And R4 is just going to have 1 amp flowing through it. So that's the current. So that's the answer to question A. So we're asked next to find the power supplied by each of the DC sources. If we know the current supplied and we know the voltage of each one, we can find out what the power is. Okay, so let's do that. So the power drawn from each sources. So power from sources is P equals IV. Now we know I1 is 2 amps. We'll just write this stuff down again because we're on a new page. I2 is 2 amps. I3 is 1 amp. And I4 is 1 amp. Also R1, we're going to need this, is 1 ohm. R2 is 2 ohms. R3 is 2 ohms. And R4 is 6 ohms. So let's work out what our 8-volt source is. We get P equals IV. So I will be I1V, so it's called P1. That's going to be 2. We know 2 amps is flowing through that guy. Times 8 is 16 watts. Our top 4-volt source, so I'll call that P2. It's I1 times V, which is 2 times, we'll call it I2. 2 times 4, which is 8 watts. And our bottom source, 4-volt source, is going to be P3, which is I3 times V, and this will be V1, V2, V3, and that's got 1 amp flowing through it, and it's 4 volts. It's 4 watts. But what's happening here, this is providing, I'll just write this, that this provides opposite work. So we consider that it has negative power. Okay, so it's pushing work back one direction, the opposite direction to the other batteries. So we can call that negative 4 watts. So therefore, the total power is 16 plus 8 minus 4, which is 20 watts. Excellent. So now, if we go and calculate what the total power dissipated by each resistor is, which is what we're asked in question C, we should find that that comes to 20 watts. So the power dissipated in a resistor is equal to I squared R. Therefore, R1 is going to be 2 squared times 1, which is 4 watts. R2 is going to be 2 squared times 2, which is 8 watts. R3 is 1 squared times 2, which is 2 watts. And R4 is 1 squared times 6 ohms, which is 6 watts. We add that all up and it comes to 20 watts. And so these are equal, which makes sense. Our batteries are supplying 20 watts and our resistors are dissipating that amount of power that's supplied, which is everything is working in physics. Excellent.